Note 4 at the bottom of Table 8 typically refers to the direct current resistance values in the table. It usually states that the values in that column are based on the International Annealed Copper Standard, also known as IX, or a similar standard. The IX is a standard for the electrical conductivity of copper. It is defined as the conductivity of annealed copper with a resistivity of 0.15328 ohms per meter gram at 20 degrees Celsius, which is 68 degrees Fahrenheit. Direct current resistance is the resistance of a conductor to the flow of direct current. It is measured in ohms and is a measure of how much the conductor resists the flow of electrons. In the context of voltage drop calculations, direct current resistance is important because it determines the amount of voltage that will be lost when current flows through the conductor. The higher the resistance, the more voltage will be lost. Wire size is typically selected based on the alternating current resistance of the conductor, which is different from the direct current resistance. Alternating current resistance is the resistance of a conductor to the flow of alternating current. It is also measured in ohms and is a measure of how much the conductor resists the flow of electrons that are changing direction periodically. Alternating current resistance is typically higher than direct current resistance due to the skin effect and proximity effect. The skin effect is the tendency of alternating current to flow on the surface of a conductor rather than through the entire cross-section. The proximity effect is the tendency of alternating current to flow in the part of the conductor that is closest to other conductors. Therefore, using Note 4 to select a wire size based on the direct current resistance values in Table 8 may result in choosing a wire size that is not appropriate for alternating current applications. To further explain this, let's delve into the details of conductivity, resistance, and the factors affecting them in both direct current and alternating current circuits. Electrical conductivity, often denoted by the Greek letter sigma, represents a material's ability to conduct electric current. Its inverse is electrical resistivity, denoted by the Greek letter rho, which represents a material's opposition to the flow of electric current. The International Annealed Copper Standard provides a benchmark for copper conductivity crucial for electrical engineering calculations. Copper's high conductivity makes it a prevalent choice for electrical wiring. Resistance, measured in ohms, quantifies the opposition a material offers to current flow. Direct current resistance remains constant under steady direct current conditions. However, alternating current resistance introduces complexities due to the skin effect and proximity effect. The skin effect arises from self-induction within a conductor carrying alternating current. As the frequency of the alternating current increases, the current tends to concentrate near the conductor's surface, reducing the effective cross-sectional area through which the current flows. This reduction in area increases the resistance. The proximity effect occurs when multiple conductors carrying alternating current are situated close to each other. The magnetic fields generated by these conductors induce eddy currents in neighboring conductors, leading to uneven current distribution and increased resistance. Now let's talk about Table 8 in the National Electrical Code, also known as NEC. This table provides information about conductor properties, including circular mil area and direct current resistance. Circular mil area is a unit used to express the cross-sectional area of a conductor. 1 circular mil is the area of a circle with a diameter of 1 mil, where a mil is 1/1000th of an inch. The circular mil area is used to determine the ampacity, which is the current carrying capacity of a conductor. The ampacity is the maximum current in amps that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Direct current resistance, as listed in Table 8, is based on the International Annealed Copper Standard and is primarily useful for direct current applications. However, for alternating current applications, it's crucial to consider the skin effect and proximity effect, which increase the effective resistance of the conductor. When performing voltage drop calculations, the alternating current resistance should be used to ensure accurate results. Voltage drop is the decrease in voltage along the conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To mitigate voltage drop, conductors with larger cross-sectional areas are often used, as they offer low resistance. In alternating current circuits, factors like frequency, conductor spacing, and conductor material affect the alternating current resistance. Higher frequencies exacerbate the skin effect, while closer conductor spacing intensifies the proximity effect. Materials with higher conductivity, such as copper, help reduce resistance and minimize voltage drop. Therefore, when selecting wire sizes for alternating current applications, consulting appropriate tables and considering the specific operating conditions is essential to ensure optimal performance and safety. Different tables and correction factors are available for alternating current calculations to account for the skin effect, proximity effect, and other factors that influence the alternating current resistance. These tables provide guidance on selecting appropriate wire sizes for various alternating current applications, taking into account the frequency, conductor spacing, and conductor material. In summary, while direct current resistance is a fundamental property of conductors, alternating current resistance is influenced by additional factors like the skin effect and proximity effect. Therefore, when working with alternating current circuits, it's crucial to consider these effects and use appropriate tables and correction factors to select wire sizes that meet the specific requirements of the application. Now let's talk about how to calculate voltage drop in both direct current and alternating current circuits. In direct current circuits, the voltage drop is calculated using Ohm's law, which states that voltage equals current times resistance. The formula for voltage drop in a direct current circuit is voltage drop equals current multiplied by the direct current resistance of the conductor. This calculation provides a straightforward estimate of the voltage lost along the conductor due to its resistance. However, in alternating current circuits, the calculation becomes more complex due to the presence of inductance and capacitance, which contribute to impedance. Impedance is the total opposition to current flow in an alternating current circuit and includes both resistance and reactance. Reactance is the opposition to current flow caused by inductance and capacitance. The formula for voltage drop in an alternating current circuit is voltage drop equals current multiplied by the impedance of the conductor. The impedance is calculated using the formula impedance equals the square root of resistance squared plus reactance squared. The reactance depends on the frequency of the alternating current and the inductance and capacitance of the conductor. To accurately calculate voltage drop in alternating current circuits, it's essential to consider the impedance of the conductor, which includes both resistance and reactance. This requires knowledge of the frequency, inductance, and capacitance of the circuit. Furthermore, the National Electrical Code provides guidelines for allowable voltage drop in various types of circuits. These guidelines are intended to ensure that equipment operates efficiently and safely. For example, the National Electrical Code recommends that the voltage drop in feeder circuits should not exceed 3%, and the voltage drop in branch circuits should not exceed 5%. Exceeding these limits can lead to problems such as reduced motor torque, dimmer lighting, and inaccurate electronic readings. To minimize voltage drop, several strategies can be employed. Firstly, using conductors with larger cross-sectional areas reduces the resistance and impedance, thereby decreasing the voltage drop. Secondly, shortening the length of the conductor minimizes the total resistance and impedance in the circuit. Thirdly, increasing the voltage level of the circuit can reduce the current required for a given power level, which in turn reduces the voltage drop. For example, transmitting power at higher voltages, such as 230 kV or 500 kV, is more efficient than transmitting power at lower voltages, such as 120 volts or 240 volts, due to the reduced current and voltage drop. In addition to these strategies, it's also important to ensure that connections are properly made and that conductors are not damaged or corroded. Poor connections and damaged conductors can increase resistance and voltage drop. Regular inspection and maintenance of electrical systems can help identify and correct these problems. In summary, voltage drop is an important consideration in both direct current and alternating current circuits. While the calculation is straightforward in direct current circuits using Ohm's law, it becomes more complex in alternating current circuits due to the presence of impedance. Following the National Electrical Code guidelines for allowable voltage drop and implementing strategies to minimize voltage drop can ensure that equipment operates efficiently and safely. Now let's discuss some practical examples of how direct current resistance and alternating current resistance affect wire sizing in different applications. Firstly, consider a direct current application such as a solar panel installation. In this case, the current is direct current, and the direct current resistance of the conductors is the primary factor affecting voltage drop. Therefore, using Note 4 in Table 8 of the National Electrical Code to select wire sizes based on the direct current resistance values is appropriate. Secondly, consider an alternating current application such as a residential wiring system. In this case, the current is alternating current, and the alternating current resistance of the conductors is the primary factor affecting voltage drop. The skin effect and proximity effect increase the effective resistance of the conductors, so using Note 4 in Table 8 of the National Electrical Code to select wire sizes based on the direct current resistance values may not be appropriate. Instead, it's necessary to use tables and correction factors that account for the skin effect and proximity effect. Thirdly, consider an application involving both direct current and alternating current, such as a hybrid electric vehicle. In this case, the vehicle uses both direct current for the battery system and alternating current for the motor. Therefore, it's necessary to consider both the direct current resistance and the alternating current resistance when selecting wire sizes. This may involve using different wire sizes for different parts of the system, or using conductors that are specifically designed to minimize both direct current resistance and alternating current resistance. Fourthly, let's consider an example of an industrial plant powered by alternating current. The plant uses a variety of equipment, including motors, lighting, and electronic devices. Each of these types of equipment has different voltage drop requirements. The motors may require a low voltage drop to ensure adequate torque, while the lighting may be more tolerant of voltage drop. The electronic devices may be sensitive to voltage fluctuations. Therefore, when selecting wire sizes for the plant, it's necessary to consider the voltage drop requirements of each type of equipment. Fifthly, consider a long transmission line that transmits power from a power plant to a city. The transmission line is an alternating current system, and the voltage drop is a major concern due to the long distance. To minimize voltage drop, the transmission line uses high voltage levels such as 230 kV or 500 kV, and large conductors with low resistance. The transmission line also uses transformers to step up the voltage at the power plant and step down the voltage at the city. The transformers help to reduce the current and voltage drop in the transmission line. Sixthly, consider a printed circuit board, also known as a PCB, used in electronic devices. The printed circuit board contains numerous small conductors that carry both direct current and alternating current signals. The voltage drop in these conductors can affect the performance of the electronic devices. Therefore, the printed circuit board designers carefully select the conductor sizes and materials to minimize voltage drop. The designers also use techniques such as ground planes and power planes to provide low impedance paths for the current. In addition to these specific examples, there are many other applications where the direct current resistance and alternating current resistance of conductors are important considerations. These include telecommunications systems, data centers, and renewable energy systems. Understanding the differences between direct current resistance and alternating current resistance and how they affect voltage drop is essential for designing and maintaining efficient and reliable electrical systems. Finally, let's recap the key points about direct current resistance and alternating current resistance. Firstly, direct current resistance is the resistance of a conductor to the flow of direct current, while alternating current resistance is the resistance of a conductor to the flow of alternating current. Secondly, alternating current resistance is typically higher than direct current resistance due to the skin effect and proximity effect. Thirdly, the skin effect is the tendency of alternating current to flow on the surface of a conductor, while the proximity effect is the tendency of alternating current to flow in the part of the conductor that is closest to other conductors. Fourthly, Note 4 in Table 8 of the National Electrical Code refers to the direct current resistance values in the table and may not be appropriate for selecting wire sizes for alternating current applications. Fifthly, when selecting wire sizes for alternating current applications, it's necessary to use tables and correction factors that account for the skin effect and proximity effect. Sixthly, voltage drop is an important consideration in both direct current and alternating current circuits, and it's important to follow the National Electrical Code guidelines for allowable voltage drop. Seventhly, strategies for minimizing voltage drop include using conductors with larger cross-sectional areas, shortening the length of the conductor, and increasing the voltage level of the circuit. By understanding these key points and applying them in practice, you can design and maintain electrical systems that are efficient, reliable, and safe.